Okay, so that's if you observe when you observe the haplotype and you count it. However, as I said, you'll come across with a high degree of probability haplotypes that haven't been observed yet in the database, and we'll talk about what that probability is. But so for that, we use the upper 95% bound of the confidence interval, 1 minus 0.05 in this case. It's 95%, 1 over n, right? And again, the databases will calculate this for you automatically. But a quick, for when you're doing it in your head, when you're doing quick calculation, the rule of threes is quite useful depending on the number of samples, etc. 3 over n would be approximately a good approximation. Now, so that's what that's the current thinking in the US has been, we do the counting method and we make a sampling correction. However, we do have to, just like in the autosomal situation, have to start considering population substructure issues. Because in the autosomal case, as everyone in this room employs theta, right? So the argument would be, if you employ theta for autosomal, why wouldn't you apply it for the Y chromosome? And it's a hard argument to say why we're not doing it. Especially since the effects of population substructure are expected, and in fact not expected, are observed to be much greater in the Y chromosome situation compared to the autosomal situation, on a per locus basis anyway. Because the effective population size is a quarter of the autosomal size, because there's only one Y. Right? If you take male and female, right, there's one Y, there's four autosomal chromosomes. So say it's chromosome 1, if you take the male and female population, there's four chromosome 1s, there's only one Y. So it's a smaller, already have it's a quarter of the effective population size. Now, it's possible that the substructure effects in a population such as the US may not be as great. Well, it's expected not to be as great because of the nature of the US population and the admixture that has taken place, and from where the individuals have all come from, that it may be less than ancestral populations. So sometimes it's not always directly transferable from the academic side from ancestral populations to use the same correction factors, theta or FST, that is found in academic studies. So in terms of the substructuring formulae, yeah, this is an older version of this PowerPoint. There must be two on here. So there's two ways of looking at the substructure. How do you correct for substructure if we were to employ it? And basically, it's P. The frequency of the haplotype could be P, which is just the observed frequency, P, plus the correction, right, based upon population substructure, theta 1 minus P. Right? Now, I said Bedoli here, but John Buckleton used the same formulation. This is why this is an older slide. But it's the same, it's the equivalent to the second. The second formulation is the same as the first, but just through algebra. It's theta plus pi 1 minus theta. Right? And I should say that there's been a recent paper that's just come out in Forensic Science International with John Buckleton, Bruce Weir, and I forget the third author. But that paper is more or less a grand summary as to where we are today, I think, in Y chromosome analysis in terms of the population substructure effects, sampling correction, etc., etc. It's an excellent, I'd call it a review article, basically. But anyway, if you look at this, if we assume that these formulations are correct, then or good enough for what we're trying to do here, theta plus pi, theta bounds, whatever theta is now your frequency. If it depends on how high it is, how big it is. So if you have your observed class, pi, here that's your observed, say that's your observed or your sampling corrected observed number of haplotypes, frequency in the observed, meaning the frequency of it in the database, we would have to adjust this by adding theta to it, right, as well as making the other calculation, 1 minus theta. So it's going to increase the observed, that value, the observed frequency. It's going to increase it. So if theta is large, say theta is 1 in 100, I'm making this up, say it's 1 in 100, and it doesn't matter what you've observed in that database, 1 in 100 is going to overrule, if it's 1 in 1,000 or 1 in 10,000 or something, that 1 in 100 would overrule that, right? So the concern would be that theta is going to reduce the effectiveness of the evidence. However, it turns out that from the studies that have been done, that basically the more loci you use, the more loci that it's used to measure theta, and measuring theta is not a trivial matter. And I would say at this moment in time, and John can chime in at any time, John, that at this moment in time, the measurement of theta is not a trivial matter, and it's not absolutely certain that we have good estimates of what theta actually are in terms of the populations that we are interested in. There has been some work, right? But anyway, the work has shown that basically if you use a larger number of loci, meaning if 17 loci versus 12, the theta is going to be smaller. And that seems to tie in with the evolutionary theory, because theta is inversely proportional to the mutation rate, and the more loci you have, then that haplotype, there's a higher chance the mutation rate of that extended haplotype is greater if there are more loci in it than if there's a smaller number of loci. So you have this diminution of theta with the number of loci. So the estimates I've seen up to now would be in the order of 1 in 10,000, that sort of amount. Now, that's not per locus, that's if you take 17 loci, right? So in theory, it could be bounded by something like 1 in 10,000 if you use the Y filer. But at this moment in time, I'm not sure if anyone in the world yet is actually using theta as a correction factor. And I'm looking at John. Do you know of anyone, John, that's using this yet? In Y-STRs, they're actually using the Y with an appropriate theta correction.
Okay, we've tabled a recommendation to make the change, and that's actually meant to happen in March.
Okay, but you'd be the first, I think, right? Probably.
It's not very hard not to be the first. I'm hoping to move the density, but density is not moving.
Yes. Okay. So we understand the theory, and this is a possibility. At this moment in time, it's not. We're in a holding pattern. It's work in progress, I would say. But I think that we have to get to grips as a community with the theta, because, as I said, it's hard to justify us not using theta. If we use it in autosomal, it's very hard to justify. But let's back up now. Let's back up and say, well, but you can never be wrong. This is the thing about certain things. If you make an observation in a database and you report that, you can't be wrong. Well, you could be wrong if you've made an error, because you've made an error yourself. But if it's a true representation of that database, if you've seen it 3 times in 10,000, that's a fact. Nobody, it doesn't matter. No statistician can challenge that fact, that you saw this 3 times in 10,000 individuals. It's when you start to then say, well, what does that mean in the population? Then the fun and games start. So you can always hold your hat. And if I was running a crime lab, I would always make sure that statement's in there. That statement's a fact. It's just an absolute fact, right? So, and it has some, and we have some legal scholars in the room here who may be able to speak to this fact, that obviously a court, can, if you say it occurs 3 times in 10,000, maybe the jury can make up their own minds about what that means. You've said it occurs 3 times in 10,000. Right, okay. Let's move on then to the Y-Str database, because we have, obviously, to be able to do these, to give some indication of the significance, we need to be able to count and use a database. There are several databases out there, and the one I want to talk about is the US Y-Str database, because that's the database that we were charged with, myself, my own group, National Center of Forensic Science, via NIJ to compile. And basically the idea was to compile and consolidate Y-Str data from all legitimate sources, right? That's what the task was. because legitimate, meaning what does legitimate mean? It's open to question. But basically we were asked, there was databases held by Promega, databases held by Applied Biosystems, databases held by University of Arizona, Reliagene, Cellmark, ourselves, etc., etc. So the interesting idea, a very straightforward one, was okay. Let's because it's a counting method, let's add them all up together and make a better database. So that's what we were charged with doing. So what we did was we set out about doing that, and we created a Y-Str consortium comprised of stakeholders and data contributors from the forensic community. We were only going to provide custodial and managerial responsibility. You know, that's what we did. We were going to have custody of it and have the managerial responsibility of ensuring that the data is released to the community. We were also developing quality indicators for data inclusion. In other words, if we're going to take data from labs, we need to ensure that the data is of some quality. We had to then, because we were going to compile data and add data from different sources, we had to screen the data and remove any duplicates, any obvious duplicates, and any obviously related samples. Does that mean that that screen is perfect? No. But what we were able to do is, because some contributors at that time, some of these databases were comprised of samples that the same individual had placed the same samples into the various databases. I can think of certain labs that were very active at the time and had contributed samples to several databases. So we had to ensure, of course, that these duplicate samples were removed. Okay, and obviously we had to ensure, we'll call it consistency among different primer sets, provide accessibility and statistical data to the forensic community via the web. So the initial Y-Str consortium that set up this database comprised National Center of Forensic Science, myself, and Lynn Fatalitis, the database manager, who's a fully qualified DNA analyst, still does proficiency tests, etc. Not in my lab, but in a lab in Florida, Trinity Solutions. She's a qualified DNA analyst. We had Applied Biosystems represented, the FBI represented, University of Arizona, NIST was represented, Minnesota Department of Health was represented with the names given there, OCME, New York City, University of North Texas, Promega, Reliagene, ORCID, and NIJ. So you can see that group is an interesting group and certainly did represent at that time, this was 2006, certainly represented individuals who had knowledge of the databases at the time and the use of Y-STRs in casework. And so what we did was we basically consolidated the data from Applied Biosystems ourselves, Promega, Reliagene, University of Arizona, removed obvious identical samples. We then, since Bruce Bedoli was on the consortium, we gave him the data to go away and try and work out, do some pop gen on it, basically theta, etc. But Bruce turned out to be very useful in this whole process, Dr. Bedoli, because he was very familiar with some of these databases in an intimate sense, meaning he knew the sources of many of the samples in the Applied Biosystems database and the Promega database. And he was able to, through his own intimate knowledge of these samples, help us actually screen out some of the obvious duplicates as well. And that iteration of screening out duplicates took quite a period of time, actually. Took several months, I would say, because you think it's very easy, you're just going to add all the data together. Ended up being much more time-consuming than we thought. But and is it perfect? No, it's a good faith effort to remove obvious duplicates. Could there be related individuals in there? Well, there must be, because there are haplotypes. There are people in there who have the same haplotype, so they are related. Just depends on how far back you want to go, because we're all related, right? But there may be some individuals in there who are related, and that's the concept of, if you were to measure theta in this database, that in some ways that could take that into account, obviously. Okay, so and we've also, what we've done then is consolidated that data and made release 1.0 available to the forensic community since January 3rd, 2008. So 2008 was made available to the community, version 1, and we've continued to kind of update that expand that database by additional samples. Okay. So this just shows basically the initial database comprised 13,900, and it shows the number of samples that were removed. 893 samples were removed from the consolidated data. That shows you how many were duplicated throughout the. So it's quite a large number. Okay, so the SWGDAM guidelines, the Y-Str interpretation guidelines, published in 2009, under Section 5 statistical interpretation, says that you should use a database. The source of the population database should be used, and a consolidated US Y-Str database, and it gives our website, right, has been established. Another one, a number of these others exist. So SWGDAM has kind of endorsed the use of this database for whatever reason. So it's actually written in the SWGDAM guidelines that this database can be used. So release 2 was made available March 2009. We expanded the samples, 17,000. Then release 2.1, 2009, 17,000 haplotypes. Release 2.2, January of last year. This is the old one. Unfortunately, this is now the old my old slides, because I had the most recent one. So anyway, we have release 2.4 now, okay, and it's in my other presentation, which is on this computer, which I don't have time to get into now. So I'm just going to briefly just describe this, if you want. Okay. So it has to go to that same slide then.
Okay.
Anyway, so the Y-Str database, we're now at release 2.4, and a few labs have contributed samples to the database. Is there any lab in this room that actually have contributed data to the national database?
Do you know where? Did you put it on the desktop or did you put it in here?
Maybe it's under there.
Are any of those yours? No.
It was taken from my stick yesterday.
Yeah, and I thought.
Okay. Okay. That's fine. I'll just.
Sorry, dear.
Because there's a couple of mistakes in this presentation. I have to remember them when I get to them. Because you have you all have I would suggest that the group, talking to the other presenters, we've all made slight changes to these presentations. I've made a couple of slight changes because I'm coming to one where I've made an error, and I have to tell you what that error is. If I don't tell you, you won't know. So I have to remember as well when I get to it, because I made the changes. Anyway, so if we go back to, let me continue my train of thought then. In terms of the number of people who contributed, there's one individual here who said yes. Yes. So we've had a slight problem in trying to expand the database, in that we've asked labs to contribute, and some labs have done, but there's been not an overwhelming kind of rush by the community to provide data to the database. But I'll talk about that slightly. Okay, so what we have on the database website is different graphs showing descriptions of the database, basically. So this here shows who contributed the data to the database. So Applied Biosystems had the most data, followed by Promega, et cetera, et cetera. You can see that. Then you have what's the composition of the database in terms of declared ancestries: African American, Asian, Caucasian, Hispanic, Native American. We have information about the loci that are present. The Y-file loci are less represented in terms of numbers, because obviously if we take data, we get data from the 12 loci. It doesn't have the 17, so there's obviously going to be less of the 17. Because the 17 will also contain the 12, if you know what I mean. Same 12 that's in Perplex Y. And here, on a per locus basis, you'll see the number of samples that have a per locus basis. The interesting thing about this database is that you can use any combination of loci to do the search. So if you have a partial profile or loci you just want to drop out, you don't have to search on that. You can search to see any combination of loci, how many times it's been found in the database. Okay? But you'll find that for each loci, they don't have equal representation, right? Because of the historical way that the data was put together. data from our lab and University of Arizona, because we may not have been using the Y-Filer kit at that precise moment in time, so we're using maybe 50 or 60 Y-Str loci, maybe 1 or 2 were missing from the so-called final set that Y-Filer had. Anyway, when the calculation's done, however, the database will say if you're putting 12 in, it will only look at the subset of data that has 12 loci or 17 loci, whatever the number is, and then count how many times you've observed the particular haplotype you're interested in. Okay, let me just bypass this. The discriminatory potential, and we're using this in loosely. If you go to the database, how many unique haplotypes are there in the database? And this is now out of date, unfortunately. But if you look at the Y-Filer here, 81% of the profiles in that database are unique. That means they occur once, only once. Whereas with the Perplex Y data, that 12, or 12, when we talk about the Perplex Y data, I mean the 12 loci, to be more correct. 40.5% of the database is unique, meaning single haplotypes. So there's 80% chance in theory, if the overall database, 80% chance that if you get a haplotype profile, it could be unique in that database, meaning it's found once, right? But it's not exactly that. That's just a rough approximation. So we have a database homepage where you can input the data, and you can search the database using. So you put your haplotype in, you decide which loci you want to use. You search by ancestry. You can search the whole database, or you can search according to African American, Caucasian, etc. If you search on all, that's fine as well, because you then get an output saying how many times these samples have been found, listing the samples in the database, and there's a database summary that gives you the count, the 95% upper confidence interval. Now it's the binomial, right, for all the different groups that you've searched. If it's all, it will give you all plus all of the different ethnic groups, or you could subdivide it to ethnic groups. The database is used continuously. The recent data I have, there's a big spike now in this last, this is now from last year, the end of middle of last year, has even gone, the rate of increases has increased. It's increased. So the M value has increased, okay? The slope has increased dramatically, but up to then it was about 800 hits per month, right? And we believe that most of that is from case-working labs, but we don't have any. Who else would be searching the Y-Str database? Maybe some of the commercial companies, ancestry companies, but I don't think so, because they've got larger databases. But I'm going to guess, based upon the feedback, that most of that would be from crime labs using it. So we've publicized the database, profiles in DNA, applied biosystems. We've got brochures, etc. And there was a recent publication again, this is, unfortunately, it's not got the proper reference, but last year, 2010, Legal Medicine. So what I'll do is I've got my presentation. It should be on here, but I have it on my stick. So I'll make it available here, and I don't know the best way of getting it to people if they want an updated version.
We'll email everybody, and there will be a Dropbox you can download all the presentations from.
Okay, because this is slightly out of date, unfortunately. But this is the same paper, just don't have the exact reference at the top here. But anyway, this is a paper published by Jianye Jeb, Bruce Bedoli, John Plants, Art Eisenberg, myself, and Ranajit. And it's basically just a description of the database, and and it does some population genetics on it, meaning it looks at theta or FST in this case. It certainly is a peer-reviewed publication that you can refer to in court. Okay, has the database been, what about database? Well, there's a peer-reviewed publication on it. Okay, as opposed to these other kind of informative, publications. So we also do what we do is for labs that want to participate in providing us samples. We do provide a sort of quality assurance exercise where we send out five blood stains of unknown type, and then if the lab can successfully type unknown blood stains to our satisfaction. We give them a certificate, and then they can contribute data to the database. So they get a certificate that says that they've successfully participated in this. They can use that in court also if you want to use it. Here's a list of some of the labs that have participated in these, and this is now slightly longer, that have taken that QC test, if you want to call it that. Obviously, for those, any samples we have in our database now must have come from one of these labs, right? Because to submit the data now, you have to pass this quality assurance kind of exercise. We have a lot of users' feedback, and we can go on and on about various feedback conversations and changes that were made to the database based upon community feedback. And it's important that the community communicates with the database manager. There's a website, the database manager, you can click on it and contact her directly or through myself, and I'll pass it on to her, most of them, if they're easy. And if they're difficult, I pass all of them on to her, right? But we do have a lot of community interaction. Okay. So I've discussed this, the Klopper-Pearson versus the normal distribution sampling correction. So I'm not going to get into this in any detail. Just I have a table in here. I was comparing in this table the exact versus normal confidence intervals using the number of observations, and say 1 in 100 in the population, or 1 in 1,000, 1 in 10,000. What the observed frequency is. So 1 in 100 at the top. That's a frequency of 1%. And then there's the normal distribution, HP, it's the Holland and Parsons, we call it, the Holland Parsons, one-tail and two-tail distribution, and then in the Klopper-Pearson distribution. But there's a mistake here. This should say one-tail and then two-tail. The one-tail's the first one, and so there's a mistake here, right? This is one of the ones I had to remember I had fixed already. But so that should say one-tail and then two-tail, okay? You can look at this at your leisure, but you can see that Klopper and Pearson, if you look down here, the Klopper and Pearson compared to the normal distribution is more conservative, meaning it's higher. There's a larger correction. It's a larger correction factor, basically, right? But as you get to say 10,000 here, say one in 10,000, it's 0.0005 as opposed to 0.003, right? Because that's 1 in 10,000. But you'll see in most instances the Klopper and Pearson is, in fact, in all instances, it's more conservative. But that's not the reason for using it. We're using it because it's more correct. Right? So what about the database itself? Okay, we've had publications on it. There's also been a couple of FRI hearings on the US Y-Str database. This particular one comes from California. There's two that I know of, anyway. In this particular case, people of the state of California versus Stephen Wesley Miskiewicz. Specifically, he contends that the statistical analysis applied in this case is faulty because of an unreliable, unknown database used to formulate the statistics. So they were after the database, the database itself. And the conclusion was, after the FRI hearing, in conclusion, upon review of Ms. Case's testimony, which the court found to be persuasive, and the literature provided to the court concerning the US Y-Str database and the statistical calculations used, the court is satisfied that accepted scientific procedures and principles were properly used in this case. Accordingly, the defendant motion to exclude is denied. So that's done. Then there's another one in October 2010, State of Kansas versus Gonzalez, and Judge Picorni, 7th Judicial District of Kansas. That's the judge. There was a challenge that over a period of 6 months, the frequency of the evidence suspect haplotype changed from 1 in 2,700 to 1 in 1786. So there was this, because this is the situation with an evolving database, which we're not used to, right, in the autosomal world, right? When we start adding to databases, and if we make changes to the sampling distribution, there are going to be slight changes to the calculation. And that's just life, and unfortunately, that's the way we have to deal with it. Or we stop at one point and just say, that's it. We've stopped and we'll never change, right? So the reason that went from 2,700 to 1,700 is a combination of two factors. One, there was an increase in the number of samples added in that period of time. And secondly, we changed to the Clopper and Pearson, so from the normal distribution. So ended up being that change. But after describing this to the judge, I testified actually over the phone for the first time in my life. I actually testified in a court. Right? I never knew that was possible, but I've done depositions, but I've never actually testified in a court of law, right, from my office. Anyway, which was quite good for travel purposes, and it saved a lot of money, right? But on 4th of October 2010, the court found that the Y-Str database is fit for purpose, and the motion to deny or exclude Y-Str was denied. Okay, so we want to continue to solicit data from labs. So I'm making an appeal to any labs out here who have good Y-Str data. If you want to contribute to the community, please contact me to see if you can contribute data to the database. Okay, so I brought my timer up here and I didn't turn it on. So how much time do I have? Okay, good. So now I want to talk now about Y-Str mixtures, okay? Now that we've come this far. Okay, so as I said, it's a work in progress. So let's consider this two-person mixed Y-Str profile here, okay? Let's just consider that this is one loci, AB, this is another loci, CD, this is another loci, EF, this is another loci, G, and another loci, HI, right? So, so you can see that at 1, 2, 3, 4 of the loci there are two alleles. And at one of the loci has a higher, double the height, it's not exactly double, but it's there anyway. You have a single haplotype, right? So this is a mix. So the question is, so you see that's a Y-Str mix, because we expect to see these loci. I haven't named them yet, but each of these loci you'd expect to find one. Now there are rare instances, just as in autosomal, where there's more than one. We don't take that into account that much in autosomal, and we don't take it that much into account yet with Ys either, right? But you can. So the number of possible haplotypes then, right, if you had this particular mix, is 2 to the n, right, where n is the number of loci exhibiting 2 alleles, right? Right? As opposed to 1, right? So there are 4 loci here, one, AB and CD and EF and HI. There's 16 possible haplotypes that can contribute to that. If you don't take into account that the 385 locus, right, which is separate. Okay. Now we can't take into account the G. We're saying no. You need thresholds, but assuming G is a legitimate signal, etc., then G obviously there's no differentiation at that locus. So when we work out the possible haplotypes in the bottom there, right? When you go down to the bottom, the 16 possible haplotypes that could be part of that mixture are represented. ACEGH, ACEGI, all combinations, right? Right. There's 2 times 2 times 2 times 2, right? In that particular instance, but not with the G. And if you look at the haplotypes down at the bottom, all 16, they all have G present because they all presumably have G present, ignoring dropout, ignoring various things, right? But that's a different issue altogether, assuming this is a profile and it meets any threshold that you've determined, right? So that's it with 2 to the n, basically, if it's a two-person mix. Now, if you then go to the database, now if you want to take into account the 385 locus, right, then the 385 locus number of haplotypes then is different because you get 2 right there. So you could say it's k times k plus 1 over 2, where k is the number of 385 peaks. If you want to, but what you should do is just write out or find out from a computer program what the various haplotypes are. So in the bottom are listed the possible haplotypes in this case, right? So if this was the case, two-person mixed, the 16 haplotypes are listed on the bottom. And what I've done on the bottom is give you the number of counts in the database. I've made it up, right? So in that database, you can see that the first haplotype that could be a possible contributor was found once in the database. The second different haplotype was found once in the database. This third haplotype wasn't found in the database, et cetera, et cetera. So most of them are found either no times or once, But here's one here that's found twice in the database, right? So in this case, we've done 2/3 of the job basically. There's a mixture present, and here's the haplotypes. There could be contributors. Finished, except we need to attach some weight, right? So the question is, what do we do? So we have now some evidence, some indication of weight now, because we now have observations in a database. That's the total database. Okay. So then, how do we attach, or how can we attach weight to that? You can just state, as I said, categorically, there are 16 haplotypes that could possibly contribute to that, of which X have been observed in the database. That's just a fact, right? I mean, as I said, you can never be wrong with that. It's a fact. Okay, but maybe they may want more, right? So, of course, again, we could approach this using either the likelihood ratio approach or the RMNE approach. Let's assume then in this case that this is a mixture then of two individuals, but one of which is going to be we can do it in two ways, but the easy one, just do the easy one, where one of the two potential donors, one is the victim, ACAGH, right? And if you look, ACAGH is one of the haplotypes here, the first one listed, that's just one of the possible haplotypes, and that happens to be the victim's type, right? And also, we have a suspect, and this suspect is BDFGI, right? And BDFGI is also one of the 16, there's one down here, right? One of the possible haplotypes. That's why if he was excluded, we wouldn't be doing the calculation to begin with, right? And the frequency of that BDFGI is 0.0034. Just let me make that up. Okay. So if we start off with just using let's just consider the RMNE approach first. Using only the haplotypes observed in the database. Count how many times, right? Each of the possible haplotypes are observed. Then sum them and determine an overall frequency that constitutes the probability of inclusion, right? So if we go back to this, there are 10 individuals. One, if you add them up, there's 10 haplotypes, sorry, that have been observed in that database, right? That could be, right? And let's assume the database is 5,000. Just make that up as well. So 10 in 5,000. So 1 in 500, 0.002. If you use the 95% binomial confidence interval, ends up being 0.00338, 1 in 296, right? So 1 minus pi is equal to the probability of exclusion is 0.9962. That is 99.6% of all males can be excluded. I don't know what that means yet, but that's we say 99.6% of males can be excluded based on this database. However, I personally find, and some have suggested that this is an appropriate way of looking at things. We haven't looked at the LR yet, but that's an appropriate way of doing it. However, how can you possibly justify not taking into account these unobserved haplotypes? Because if you find a single source, we take that into account. If we have a single source sample and we haven't observed it, we give it a frequency, right? We don't ignore it. So some people who are suggesting that we should use this first approach are ignoring the possibility that there are the likelihood that there are many unobserved haplotypes that are present in the human population, right? Now, as I said, it's more complicated than that because many of them will not be observed in the human population. That's an issue that, so either you can be conservative and say, we'll just take into account the fact that they're unobserved and we'll give it 3 over n, so to speak, or we have to have some evolutionary genetics, phylogenetic approach that will say, we'll only take a certain percentage of these because these can exist in human population, but these can't. That's difficult. So anyway, let's just take a conservative view and say, let's now take into account the seven haplotypes that could be components of the mixture, because 7 of them, 1, 2, 3, 4, 5, 6, 7 of them didn't have any observations. So there's 7 of them. If you just say it's 3 over n, just for quick calculation, 21 over n, 21 over 5,000 is 0.0042. So you can add that 0.0042 of samples, sorry, of haplotypes that haven't been observed in the database. We can then add that to the observed class, 0.0338. So you end up with 0.00758, which is 1 in 132, right? And so if you do the PE, it's 99.2%. So by taking into account the unobserved, the classes of haplotype that could be part of the mixture that are unobserved in the database, then it's 99.6%. So it's 99.2% are excluded versus 99.6% otherwise. So there's a difference, right? From 1 in 296 people to 1 in 130 people. Now, this is just used as an example. I can imagine situations where the discrepancy is much greater than that. Because I've only used a small number of loci here, right? Not 17 loci. So, so alternatively, we could look at the likelihood ratio approach. So you have the prosecution, LR is the probability of the evidence given the prosecution hypothesis versus over the probability of the evidence given the defense hypothesis. So the prosecution hypothesis, in this case, this same case, is that there's one known and one unknown, right? Now, we could do the two unknown, but we may as well use the same scenario here, the one known, the victim, and the unknown. So in this case, assume the victim plus the suspect DNA comprises the mixture, right? We have the known victim, and we now have the known suspect, right, that has just come in, and he has that, the haplotype I just told you about, and so that probability is 1. Defense hypothesis is that the mixture comprises DNA from two random unrelated males. Now we could say it could be from the victim plus one let's just do two random unrelated males. So what you can do is here's all the haplotypes, right? And here's the count in the database, and here's the frequency of that haplotype, probability of that haplotype, with the binomial sampling correction listed. So for one observation, it's 0.0034. For two, it's double that. And for zeros, they're all the same at 0.0006 because they're unobserved. Right? So there are 16 combinations of haplotypes that can produce the evidence. It turns out there are 16 combinations of these haplotypes that can produce the evidence haplotype. And when you work out the frequencies of these, then you can see that it's 1 plus 16. Haplotype 1 plus haplotype 16 can give the totality of the haplotype, right? Meaning that each of the loci, that all of the alleles can be explained by the two individuals. Okay, so it ends up being. And here's the calculation here: all the different combinations, etc., etc. You just, 1 plus 16 is the probability of 0.0034 times 0.0034. Right, because it's the probability of, this haplotype and this is the probability of the two of them together. The likelihood ratio calculation is 1 over 2 times this expression here, and it's 1 over 2 times that number I just did there. It ends up being 9,419. Okay, so the DNA profiling results were 9,419 times more likely for a mixture comprised DNA from the victim and the suspect than if it came from two random unrelated individuals. Now, remember, that's not exactly a true statement because we're dealing with databases here, so we'd have to work out how we would say this properly in a database format. So now, when you have the likelihood ratio, of course, you've got certain assumptions. The assumption was then that it was a victim plus the suspect exactly, as opposed to two random males in that database. Or you could have said, but of course, one thing just occurred to me actually that when we talk about victim and suspect here, obviously the victim has to be a male, right? So it just occurred to me to say that it's not a sexual assault case with a male-female. Anyway, so you can see that in this case the result ends up being 9,419. So to summarize then, when you try in this pretend case, the RMNE gives a result 1 in 296 of individuals could contribute, of the males in that database can contribute. to the samples, or 132 if you take into account unobserved haplotypes. Now, they're not in the database now, they're possible haplotypes in the population, right? The LR, the DNA results are 9,400 times more likely if the suspect is admixed with the victim than if DNA from 2 random males' DNA is present. So, so there's differences, but of course there are 2 different questions that are being asked there. Now the question then becomes so what? This is one, you could do this, but should there be population substructure correction added? Most of the talks I've heard up to now with the autosomal don't even employ the theta correction, right? But some do. But then, because you're often not looking at genotypes, you're not actually looking at the individual genotypes. You're not deciding if you're not always deciding, but you can do. But not all of them. Not all of the talks. Not everyone uses population substructure corrections in autosomal. So should we use this substructure correction instead of or in addition to the binomial sampling correction? Some individuals have suggested that instead of the denominator of a likelihood ratio, instead of haplotype frequency, some suggest use the frequency of pairwise haplotypes from the database that can explain the mixture. So if you take all pairwise comparisons in that database, and so you have a database of n, you could do the number of pairwise comparisons to see how many of these pairwise comparisons, once you've listed them out, how many of them could explain the evidence. And in this case, it would be if we use the same numbers, 5,000 sample, it ends up being that without the binomial correction, it would be 8 observations out of a small number, and so the likelihood ratio here would be in the order of 1 million or something, which to me just intuitively doesn't make sense to me, actually. So again, my point is that there's so many factors that we have to consider in terms of performing the statistical calculation of a mixture that I don't think there's a consensus yet in the community as to the only way or the best way to actually do mixture calculations. You can certainly determine the presence of a mixture, certainly determine the potential haplotype contributors, and you can add them all up, right? But it's these other issues that we haven't yet come to grips with yet, and I think it's still a work in progress. Okay, the US Y-Str Database does have a couple of mixture tools present on the website, and these mixture tools do not do what I've just described, right? I believe there's 2 of them, and I believe there's been some problems, I understand. I haven't heard, I just heard a rumor, but the database manager should be informed that some of them are not working properly at this precise moment. But I'm more familiar with the Cal DOJ one, the California Department of Justice one. Is anyone here from Cal DOJ? No. So this tool was provided by Steve Myers, and it's available on the website, but if there's a problem, we can certainly send you a copy of this directly. But what this tool is good for, it certainly can deconvolute the number of haplotypes and count how many haplotypes have been observed in the database. So if you have a mixture, you can plug in the data, and it will give you back how many haplotypes that could be contributors to that mixture have been observed in the database. It says nothing about the unobserved classes, right? So it's a tool for doing this. So you have to decide whether you can report this data knowing that there could be an issue with the unobserved classes, or you can just add the unobserved classes, or you can do what you have to do. But that tool, so it's pretty good at deconvoluting the possible haplotypes, because that can take time if you're doing it manually. So I think this is an excellent tool for that. But it's not a solution. It's only a tool to be used for that purpose. And what we do with this one is this is an updated version. So in other words, the version on the website will be version 2.4 of the database. When we update the database, we give the data to Steve, who updates this software. Right? So it's not impossible that there could be some bug or something that when he transfers it, there could be a bug. We have to be told about that so we can fix it if any of you found any problems. There is another one from Harris County, MEO, Y-Str Mixture 2, and I think there's been some problems with that. So with that, I should like to. I'm sorry I couldn't offer you the security blanket of a total solution for Y-Str mixtures, but I believe that The community, the international community, and certainly in the US SWIGDAM, I think it's time that SWIGDAM now, as it's supposed to do and it has on the agenda, should start to address the question of the interpretation of Y-Str mixtures. And I'm very confident that this will in fact be addressed by SWIGDAM. But unless we have a SWIGDAM security blanket document, then we are basically, you have to make your own judgment as scientists if you have to deal with Y-Str mixtures. So with that, thank you very much. So any questions, folks, or comments, or? Wow, you kidding me? This last thing here, just, okay, I'll finish then. That's a little place in Scotland, actually, you're driving down the road, and it says, Strome Ferry, no ferry, It's a place called Strome Ferry, and apparently all the tourists think there's a ferry there, and they all drive away down it in this tiny village, and they can't turn back, they can't get back, there's no ferry. So they have a long line of cars that are stuck down there, so they have to put a sign up, Strome Ferry, but there's no ferry, sorry. I don't know why I did that, I thought it was just funny, that's all.